to talk to you about power factor correction. And oddly enough, I have a piece of equipment here in my shop that we can use to try and demonstrate how we can improve the power factor of the motor that's providing me the power to this particular tool. Now, power factor correction is basically taking a look at the efficiency of the motor and trying to feed the motor with all of the reactive power it requires in order to function. The benefit to you, the homeowner that pays a utility bill, is that I can show you how to lower the cost of operating this particular motor. Now, in some cases, and I'll be able to demonstrate that today, I can actually eliminate up to 60% of the current that this motor is going to require to operate. And I said that correctly, 60%. This is a single-phase induction motor, and I'm going to show you a couple things about this. Some of you may have noticed that this particular motor already has a capacitor, but let me assure you that the capacitor that is tied to this motor is used for the startup of operation and in no way contributes to the energy efficiency of the motor. In fact, what I've done is I've gone out and have purchased a capacitor for just that purpose. But before we do that, we've got to do some homework. Namely, I've got to get some of the information from the motor's rating plate. We'll do a close-up so we can show you exactly the pieces of information we're going to need. Now, the motor's rating plate is going to provide me with pertinent pieces of information such as the horsepower rating, the applied voltage, the power factor, as well as the efficiency rating of the motor. These are all details I'm going to be required to factor into my calculations. So here at the college, I'm going to make use of these whiteboards in order to do our calculations for this Leeson motor. Now, I've taken the liberty of writing down all the pertinent information that I need that's going to let me do my calculations. Namely, the input power, quarter horsepower. Now, we're going to have to do conversion because this is the old English method of ranking motors. The applied voltage to the motor, the frequency, because we know that capacitors are sensitive to frequency, the efficiency, as well as the power factor. Now you can see, looking at the power factor and the efficiency, that this motor is an ideal candidate for doing power factor correction. I mean, an efficiency of 56%, we've got an awful lot to work with here, as well as for the power factor. Now, for those of you that are inclined to wonder, the current, the FLA of the motor was actually rated at 5.4 amps. Now that's particularly high for a quarter horsepower motor, but it's also a motor that has an awful lot of torque. Now, we're going to start with step one. Now the first step in this is to take this older English value of horsepower, and I got to do a conversion into, I don't know if it would be called metric, but we're going to convert that into watts. So first thing, get my marker here, is convert into watts. Now the conversion, 1 horsepower is equal to 746 watts. So in our case, what we're going to do is take a quarter horsepower, it's 0.25 horsepower, because we're going to have to use decimals in order to do this calculation, and we're going to multiply that by the 746 watts, which is our conversion factor, and I'm going to get for an answer 186.5 watts. Now, that value represents the output power at the shaft of the motor. Meaning, when the manufacturer put their stamp and said that this motor was rated for 2 or 1/4 horsepower, that is implied that that's where the output of the shaft is. But it doesn't take into consideration the extra energy that the machine had to take in order to give us this output. So we have to take into consideration the efficiency losses, meaning we've got areas with friction in the bearings, the fact that you've got magnetic flux traveling through a small air gap, and air is an insulator. So we've got some losses that contribute to the fact that this is not a very efficient motor. As well, this motor is operating on single-phase power, and that's one of the big reasons why single-phase motors suffer from poor efficiency. They're using a single sine wave. So we're going to go ahead and jump onto step 2. Now, to make things a little bit easier, I'm going to move down onto this other board and just keep moving along. Now, our next step is going to be to calculate the total input power. That means then, is now that I've done the conversion from horsepower to watts, I have to allow for the efficiencies of the motor. So when we call that total input power, now it's easy as basically taking your TIP, it's equal to your watts divided by your efficiency of the motor. So in this case, we're going to take what we just calculated, which was 186.5 watts, and we're going to divide it by the efficiency. Now the efficiency, we don't remember, it was 0.56 for the efficiency. Now I had to convert this into a decimal form in order to be able to do the calculation. I couldn't put percentages here. Now, putting this into a calculator, you should be getting, as a result, 333.04 watts. Now, it's important to remember that we're still working with the value of watts because it is still considered to be power. Not apparent power or reactive power, it's still power. So that's why we had to give it its own unique name. It was total input power to differentiate from the first step. So now that we've got our total value of input power that does incorporate the loss of efficiency, now I can actually use this to start figuring out the apparent power of the circuit. So that's where we're going next into step 3. Total input power, 333.04. Next, we're going to calculate apparent power. We're moving on to step 3, calculating the apparent power of the motor. Now, to do this, what we're going to do is take the listed value of power factor, and I'm going to divide it, the total input power, and that's going to give me the apparent power of the machine. Now, apparent power, that means then that we're taking into consideration all of the reactive power and the true power the motor requires. And this is a really important step in understanding how to calculate for power factor correction. So let's start plugging in our numbers. 333.04 watts. We're going to divide it by the power factor, which was just over here at 54. So 0.54 was the value of power factor. Pop that into a calculator, and what we should be getting for the apparent power is going to be 606.73 VA. Now, it's important to note to keep track because we're going to be doing another step that's going to look an awful lot like this. This is the actual values. In our calculations, we're also going to be calculating for the desired value of apparent power, and that's coming up shortly. So what I'm going to do next is I'm going to go off camera, I'm going to erase this, and we're going to proceed to step number 4. I'll be right back. Apparent power, now this is an actual value, 616.73, and now we're going to proceed to calculating reactive power. Moving on down to the board. Okay, we're moving to step 4, computing for the value of reactive power. Now that I've calculated for the apparent power of the motor, and I also have the total input power of the motor, I can use those two values to help me calculate for the amount of reactive power the motor requires. Now, the reactive power basically becomes the amount of current required to magnetize the core of the motor, because an electric motor is a magnetically operated machine and it needs reactive power to create that magnetic field. So, and that's what power factor correction is all about, trying to establish how much reactive power I could feed that machine, but not coming from our power supply. So, first step, we got to find reactive power. Now, we're going to take the value of VA, which we calculated previously, and that was 606.73 VA squared. We're going to subtract that total input power, which was 333.04, and that was watts squared, square root, and VARS sub L, which is your reactive power, should be for a value or as an answer, 519.08 volt amps reactive and inductive. Now, I also want to put a little note, these are actual values. So this is the amount of reactive power the motor needs. Now, we're going to move on to another phase of our calculations, and now what we're going to do is step into calculating reactive power and apparent power, but for the desired power factor. So stay tuned, I'm going to be right back. Now, that sums up everything for the actual values. Now we're going to start calculating for the power factor that is desired. So we're going to move down and we're going to start recalculating for apparent power, but at this 95% power factor. Now, this is the next step. We're going to recalculate for the value of apparent power, but now we're going to calculate it for the desired power factor. Now, it is an industry standard that we calculate for a power factor of 95%. The reason being, as electrical workers, we work more in ranges than we do in definite numbers. Meaning, I could take a reading of an electrical circuit at any point during the day, and I'm never going to see 115 volts, 0.000. It doesn't happen because there's going to be some fluctuations, and that's one of the principal reasons why we are calculating for 95%. We're leaving ourselves a little bit of wiggle room to allow for fluctuations in my input voltage or if there's some line loss. So this is where it's better to have a slightly lagging power factor than have leading. If I oversize my capacitors, I'm actually going to have an excess of current, which is something I want to avoid because our metering equipment in our own homes will register that as extra current, but not as a surplus. And you end up paying more for your electricity. So this is something we want to avoid. Now, the formula is, we're going to take the total value of total input power, and this is a value that doesn't change in our calculations. So this is going to be used again, but now we're going to divide it by the power factor that we want. So we're going to take the 333.04 watts, and I'm going to divide it, now we're going to put this into a decimal form, 0.95, which again is your power factor that is desired. And you should be getting for an answer 350.5, pardon me, I meant to put 7 and I started to draw a V. 5.7 VA at 95% power factor. So I always found it important to make sure I properly annotate these values so that I can avoid any kind of confusion during the process in which I'm doing my calculations. I hope that you'll do the exact same thing if you're following along at home. Okay, parent power, 350.57. You know, there's a real big difference here in the values of the parent power after we've done power factor correction. It's really going to be interesting to see how much capacitance it's going to take. But enough about that. Let's move on to calculating the reactive power for this new power factor that we're calculating, remembering 95%. So we're moving into step 6, where we're going to recalculate the value of reactive power, but now for the desired power factor of 95%. The process is exactly the same, it's just that the values are slightly different. So when we write up the formula, we're still putting in bars L, but I'm just putting in the reminder that at 95%, I'm still going to take the value of apparent power, but it is the apparent power at 95%. That's the value I'm going to use. And I'm going to subtract that total input power. And again, square, square, square root. Now, let's put in our values. So we had calculated that new value of apparent power at 350.57 VA squared, subtracting, again, that total input power. That value doesn't change at all in this procedure. 0.04 watts squared and square root. We'll input this into a calculator, and the result is going to be 109.46 var sub L at 95% power factor. Now the significance of this number is this is the amount of reactive power I'm going to allow the motor to draw from my power supply. The remainder of that reactive power has got to come from my capacitors. So that's our next step. Our step 7, we're going to calculate how much reactive power I need to get or obtain from a capacitor. So this value represents the amount of reactive power that we're going to allow the motor to draw from our circuit once we've done power factor correction. Now this is going to fluctuate, but you can see that it is basically, was it 20% of the original value. So now we're going to go and calculate for the amount of power we need to obtain from those capacitors, or capacitor in this case, because we only have the one motor. So we're going to go and do that next. So our next step, we need to figure out how much reactive power is going to come from the capacitor. Now I'm going to use the value of reactive power from our previous calculations, as well as the actual value of reactive power. So the formula looks a little bit like this. So your vars C is equal to your vars, and we'll put down the actual value, and we're going to subtract the vars L at 95%. So there's no trig formula, it's just a straight up subtraction. So in this case, I'm going to have to check my notes here. What we're going to do is take the 519.08 vars, subtract that 109.46, and the result should be 409.62 vars capacitive. So this is the amount of reactive power I need to be able to generate using a capacitor. Now, it's just a simple matter of using the applied voltage to calculate how much capacitive reactance and finally the value of capacitance. I'm going to erase this and I'll be right back, and we're just going to keep trucking on to steps 8 and 9 respectively. So this is the amount of reactive power that we need to obtain from a capacitor. And now it's just a simple matter of taking this value of power and now breaking it down into individual values so I can obtain a value of capacitance. So let's just keep moving on. Now moving to step 8, I've kind of jumped a step in the sense that I have the value of reactive power, and I could have gone an extra step and calculated for the value of current and then use that to calculate the value of capacitive reactance. I just figured most people understand the Ohm's law wheel, so I just proceeded to finding the value of capacitive reactance using this formula, where I'm going to take the applied voltage squared and I'm going to divide it by the value of reactive power that we've just calculated. So in this case, we're going to take the 150 volts, which was the rating on the motor itself when I got the given values, and then we're going to take that value of var C, which we just finished calculating, which was 409.62 var sub C. Putting that into a calculator, you should be getting, as a result, a capacitive reactance of 32.29 ohms. And like always, any of the calculations that we're doing, we always round to 2 decimal places, which is a standard in the program here at Cambrian College. So we got a capacitive reactance of 32.29 ohms. Now, all it requires us is to calculate for the value of capacitance. So we're almost there. And now we're moving to our last step. We're going to find the value of capacitance. Now all we're going to do is we're going to take this formula that is commonly found in electrical textbooks, where it's 2 times pi times the frequency times the value of capacitive reactance and 1 over. Now there is a bit of a shortcut. We're doing this calculation here in Canada or North America, and the frequency that we're working with is 60 hertz. If we plug 60 hertz into this, you'll actually get almost as a constant value 377. So let's draw this out again. 377 multiplied by our value of capacitive reactance, which was 32.29 ohms, and then 1 over, or the reciprocal. Now that is going to give you, as a result, 82.15 microfarads. Now oddly enough, my research has revealed that you can indeed purchase an electrolytic capacitor at 82 microfarads. They also make them in 80 microfarads, but they're a little bit harder to find. So I went shopping at a local HVAC dealer here in town, and I picked up an 82
a microfarad capacitor, but the range on it is because the tolerance is plus or minus 20%. So what we're going to do is proceed down to the shop, and we're actually going to go and put this to the test. But before we do that, I want to do one last step. It would be nice to know, after I've done the power factor correction, how much current would I have eliminated from my power supply doing power factor correction. So I've got one little calculation to do. As a supplement to the calculations we've just done on power factor correction, I was kind of curious to see how much current could I have gotten rid of once I've done my power factor. So when I go and install the capacitor I have just calculated for and sized it, what kind of current am I going to see being drawn from the system? So it's basically Ohm's law, but I'm taking the desired value of apparent power after power factor correction, and I'm going to divide it by the voltage that was listed on the nameplate of the motor, which was, in this case, 115 volts. So let's take that value of 350.57 VA, and we're going to divide it by the 115 volts. Now, this is going to give us a rough idea, because typically we have 120 volts, and when I've taken readings, typically, depending on time of day, it could be as high as 122, 123. But this is going to give us a good general idea. Now, inputting these values into a calculator, I got as an answer 3.05 amps. So, when we started out originally, the original value was 5.4 amps. So, in theory, I should have eliminated at least 2 amps of current. So that means then that I'm going to see a savings over the apparent power, and based on the cost of a capacitor, which typically will run you about $12 to $15, it'll take me less than a year to recover the costs I have spent on doing power factor correction for that one little motor. So now that we've done this, let's take a walk and go back to my garage and see how this was going to work out for us. Now, in order to facilitate things, what I've done is I'm going to employ this line splitter. Now, this device is going to allow me to plug it into our power supply, but it's going to allow me to use my clamp-on ammeter to get a current reading. I want to get current readings prior to doing any kind of power factor correction so we can get a baseline reading, and then after we've done our power factor correction, we're going to check the current again and see how much current we were able to eliminate coming from my power supply. Now, the first thing we're going to do is we're going to energize the motor. I've disconnected the belt in order to lower the noise during filming. I'm going to turn on my ammeter for AC current, and we're going to take a reading here. I'm going to get an actual value, and I'm getting about 5.02 amps. So I am going to hold, and we're going to lock that value in. Now we've turned off the motor, I can proceed to wiring in the capacitor. Now, for the sake of safety, we are going to disconnect from the power supply. I'm going to move a few things out of the way. We're going to open up the connections, and I've already pre-wired the leads. Now, a power factor here we go. Now, I'm just going to take off my electrical tape here, made sure that
there weren't going to be any sparks during my demonstration. Now let's see here, where's the end? Oh, here we go. Now, when we wire in a capacitor for power factor correction, we wire the capacitor in parallel with the motor. So if we take a good look at these leads, you'll see here is the hot or the black conductor as well as the neutral. And so I've got two leads running in parallel. Here's the capacitor. Now we calculated for a capacitance of 82 microfarads. Now I went locally and I was able to purchase this capacitor from an HVAC dealer. And the only thing is that this capacitor is actually rated in a range from 72 to 88 microfarads. With capacitors, they have an area of tolerance of about plus or minus 20%. This is all that was readily available. Do they make capacitors with a higher tolerance? Yes, they do. Typically of plus or minus 10%, and I've seen them as high as 5%, but you're going to pay a lot more money for them, and they're not easily obtained. You're going to have to order them and probably wait a while before you get them. So this is the best I could do on short notice. One other thing is that this capacitor is rated for a maximum voltage of 250 volts, which is more than enough because we're working with an input of 120 volts. So nothing bad is going to happen. So we're going to go ahead and we're going to wire up this capacitor. Now I'm using solderless connections. I'm just going to clip that on, clip this on, and now I'm going to reconnect my splitter and my actual power supply to the machine here. Now I did take the belt off just for the purposes of this demonstration due to the fact it creates an awful lot of noise. So we're just about ready to go and turn the power back on. I'm going to set up so I can get a better picture of the value with my clamp-on ammeter. What's really nice about this splitter is I've actually got a convenient location to test the input voltage to make sure that everything is going to be accurate. So if I take a reading, and we're going to hit the hold function. So currently, when I turn on the power, the motor is going to be fed with 124 volts. Now that's slightly higher than the 115 volt rating that we found on the motor's rating plate, and that's going to affect the current as well as the power factor. Now before I turn anything on, we can still see the previous reading in the memory of my ammeter. I'm going to go ahead and erase it. So we had a previous reading of 5.09 amperes. Now let's turn on the power, and we're going to get a new reading. Now in theory I should have eliminated an awful lot of that unwanted current, and look at this. I've actually am reading about 2.1 amperes. So let's hit the memory function. You'll notice that the machine or the motor is not making any kind of odd noises. As far as it knows, nothing has changed. The only thing that has changed is right here. The motor is drawing about 3 amperes less current than it was previously before we put in this power factor correction capacitor. I had worked the numbers and I've eliminated 63% of the current that the motor was drawing previously. Now that's a substantial savings. You'll notice the machine is operating at the same speed as it was previously. It's not making any more noise as it did previously, and it did not affect the horsepower. What is? But you know what? Let's go and put the belt back on. You really gotta love these older machines with solid cast iron. They don't make them like this anymore. Now, I've got the belt back in place, so I'm going to turn the machine on and let's see if it has any kind of effect on the operation of the machine now that I've added power factor correction. Okay, here goes. Well, if there's been any changes in the operation of this motor, I can't find it. If anything, the only thing I've done is I've eliminated an awful lot of the current that the motor was drawing from my power supply previously. I'm hoping you enjoyed today's presentation. If you enjoy these videos, please hit like and subscribe to my channel. As well, I really had a lot of fun putting this together, and hopefully you found it interesting. So until next time, stay safe.